With all of the construction that's been going on the solar cars, we haven't had a lot of time to stop and take a break and talk about some of the lab reports and some of the other kind of conversations that we've wanted to have about other labs that we've done this quarter. So this video will kind of summarize some of those topics just in case you're absent or we don't have time to talk about one or two of these topics in class together. So first, just to start off with the work and power lab, one thing I wanted to go over really quickly was powering a light bulb. Pretty much everybody understood that walking up the stairs slowly, if you're producing about somewhere in the range of about 100 watts of power going up the stairs, you can power one light bulb. If you are going up, you're running up and you're producing 400 watts, you can produce 4 light bulbs, right? Assuming they are 100-watt light bulbs. What I really wanted to point out here is not this, mathematical conversion, but that clearly we can produce a lot more energy than a single light bulb, right? We are very powerful. And that was also just running up the stairs. We can do things that actually need more power, right? We can pick up really heavy objects. We can throw really heavy things. We can produce a lot of power. So humans have like a high power max in a short burst. But what's interesting about machines is that they can do it all day long. So forever, right? They can go forever, assuming that the electricity doesn't go out or that the power plant doesn't shut down or we don't run out of coal or oil or whatever we're burning, right? Humans, we can do a short burst of a lot of power right then. However, machines can just run at that 100 watts from now until the electricity goes out, which is hopefully never, right? So that's kind of the key difference there, is that humans have a really big short burst, machines can go and go and go. And also remember, in the long run, we're talking about a 100-watt light bulb. A car engine can produce a lot more power than us. So really, while we might have a big short burst, some machines can provide an even bigger burst and then also run for however large that gas tank is in the car. When we're talking about how, the work never changes, right? If work is force times distance, we want to remember that the work is the job done. So whether, when we were talking originally about it like a month ago, we were talking about you've got a box outside on the moon court, you need to move it up into the classroom. You've got two ways of doing it. You can pick up that 200-pound box and throw it overhead through the window and into the classroom, or you can drag it, across the courtyard, up the stairs, down the hallway, and into the room. So realistically, the work is exactly the same. The end job, you get that box into the classroom. Which one is easier, which one is faster, might be a whole different conversation. That gets into power, but we're talking about the job that's being done. When we're talking about the stairs, the force is your weight, and the distance was the number of stairs, neither of which change. One thing that a lot of people forgot to talk about, whenever we're in our discussion section and we're explaining the results, we want to explain all of the results. So we would want to talk about slow, fast, which most people did both of those, and then fast 2 at a time, right? And a lot of people forgot to talk about this one, which was interesting because you're not necessarily running any faster, right? It's not like you are going slow at fast and then at fast 2 at a time, you're actually like trying harder. It's just that you are covering 2 steps in every single, or 2 stairs in every single step. And if we think about the biomechanics of running, every single time that you take a step, it requires time. It actually requires you to slow down, because every time that you touch the ground is a time when you're not flying forward. So if we can eliminate the number of times that our feet touch the ground, we will actually be covering a greater distance in a shorter amount of time. To switch gears here, to talk about the fan cars, one thing that I think confused people was adding on the shield, right? And kind of how to draw that and how to explain it. So if this is a normal fan cart, right? If this is the front and that's the back, that means the air, the fan, as it spins around, the air comes through here. That would be our action force, right? The air travels through here, bounces off the other air molecules, and then hits into the fan itself and the car itself, pushing the car's motion in that direction. So these would be reaction forces, right? And yes, I know there's 3 reaction forces. I'm just trying to show that they're all bouncing off of these individual molecules, right? This big action force comes through and it bounces off of these molecules and redirects it out to the car, sending it in that forward motion. Now, the fan does something different. It's actually going to switch which is the front and which is the back. We normally expect the car to be going in this direction, but that doesn't happen because as the air travels through here in our action force, right, it comes through the fan, it's immediately redirected, where it then hits the air molecules and bounces the car in that direction. So if this is the action force 1, right, this is the action force 1 moving through the car, bounces off the fan almost instantaneously. And this is reaction force 1, reaction force 1, and then these are kind of reaction force 2, right? So what's interesting is a really good way to describe this is you've got a tug of war, or you have a push and pull kind of going on here. This action force that comes through and then bounces and transfers into this reaction force is sending the car a little bit in this direction. So there's a little bit of motion heading that way. But then that reaction force comes back and actually kind of turns into an action force, hits against these air molecules, and is redirected once again into a second reactionary force, sending the car actually like that. So if we have a little bit of motion heading to the right and a little bit of motion heading to the left, what's going to happen in general? If we're thinking about this in terms of vectors, vectors heading in opposite directions would subtract. And if they're going to subtract, that means that the speed is going to be slower, which is what we found. When we put the fan or the shield on the fan car, we not only found that it reversed directions, but it moved slower, right? And realistically, that's happening because of these vectors, because of this tug of war, this push and the pull, where this action force immediately is redirected, and then this reaction force of the air hitting the molecules, the other air molecules, bounces back against the car, and eventually sends it in that direction. But this little tug of war between these two motions, between this set of reaction forces and this set of reaction forces, 1 and 2, that tug of war causes it to go slower. So talking about all of that in some way would be a 4 type of answer, right? Really talking about this tug of war, talking about how there's 2 reaction forces, or about even how the action force and reaction force are reversed because of the fan, right? Even if we didn't really think about how there's a reaction force 1 and 2, right? How this reaction force 1 almost becomes a second action force. Even if we didn't go into that, talking about the reversal of the action and the reaction force, because essentially this shield is so close to the fan that this action force is immediately just redirected, right? And a little bit of it is spent in this motion here, leading to this tug of war. Skipping down, gears versus pulleys. This is something I think we've all touched upon in every class. Gears are faster. Pulleys are a little bit slower, not by much. And the reason for that is because with gears, we have, I'm going to draw a really terrible gear here, the teeth of this gear and the teeth of this gear actually fit in like that. And that causes a lot more direct contact. So when these two gears are spinning, there's no slippage. But when you're using pulleys and those rubber bands around the two pulleys, that's going to be, you're going to lose some of that traction. You're going to lose some of that because the rubber band's not going to always be tight enough to be, for the motion of the pulleys to be transferred directly to the axles. Here, if these two gears are close enough to each other, there's no way for these to slip out of each other because of the size of the teeth. The one problem with the gears, though, is that they're very difficult to get lined up exactly so that the teeth mesh perfectly. Gear ratios, we talked a lot about, how in that transmission lab that we did, small to small was the fastest of the three options that we played with. If we're talking about this is what's on the motor and this is what's on the axle. However, theoretically, big to small would be even faster. We're going to talk about why in a second, but just kind of one caveat to this is that big to small requires a lot more torque from the motor to get that big gear going. So on the solar car, big to small theoretically is better if the rest of your car is built with very little friction and very little weight. However, if you're having problems with traction and friction and weight, small to small will be your best bet if the big to small isn't working well. So I'm going to erase this one right here. If we're looking at big, so here's what's on the motor and here's what's on your axle. If we think about this, if this one, which is attached to the motor, if it turns a quarter of a turn, and we measure the length of that quarter turn, this small gear will turn completely one time. So 1/4 turn of the motor should theoretically turn your axle one time. So if it turns your axle one time, that's going to move your car forward a greater distance. If instead we were going big to big, and this turns, let's say it turns a half, this one would turn exactly 1/2 as well. So your car would go a half as far. If this is option B, option A would go actually goes once, here it goes, actually we're not doing that even, hold on, let me change the math so that we can do a better comparison. If this turns a quarter, this would turn a quarter, and therefore option A would actually be 4 times better. You don't need to understand how to calculate that or anything, but just understanding that when this big motor turns, when this big gear turns, it's going to turn this smaller axle a full 1 revolution versus over here, it would just be a quarter and a quarter. Finally, for graphing, the last thing I'll say here is if you are losing points on graphing, come and see me. This is going to be on your next test. It will be on the final. If you are still losing points for silly reasons on your graphs, come and see me. Your title must be descriptive. You must have units, right? So that would be like newtons, joules, something like that. You need to have axis labels. So that would be like force. That would be work. And that needs to be on both the X and the Y axis. So if you're still confused about why you're losing points still, come and see me. Let me know if you got any other questions.